Hey everybody, we're back and we're starting section 3 of chapter 3 today. We're talking about function operations and compositions. And our goal today is to perform an operation of two functions to model a biological process of a rhino. We'll do that at the end. So let's still go ahead and talk about our operations of functions. So there's four of the most common mathematical operations are addition, subtraction, multiplication, and division. And the way that it looks in the context of functions would look like this. So let's say an overall function, we'll call it h of x. You could really have any letter. You could have j of x, m of x, doesn't matter, equals some function added to a different function. So let's say, for example, in all of our examples, we'll say f of x equals 5x and g of x equals x plus 2, okay? So for example, if I had f of x plus g of x, I would literally take what f of x equals, which is 5x, and add it to g of x, which is x plus 2. And then we just combine like terms here because we're just adding in the middle. So 5x plus x plus 2 equals, now here's our like term, so we've got 6x plus 2. All right, let's go on to our next one. So subtraction could look like, so the subtraction function could equal f of x minus g of x. And if I were to do the example, f of x is 5x minus whatever g of x is, which is x plus 2. Now keep in mind, just like we did before, this minus is going to go to both parts. So we're going to go 5x minus x and 5x minus 2. So when we do this, I like to distribute it through everything behind it. So make it a positive, and then everything behind it becomes an opposite. So we've got 5x plus a negative x, or just minus x, and plus a negative 2, which is just minus 2. So we're left with 4x, because these are like terms, minus 2. All right, let's look at multiplication. So this is when we would have two functions multiplied by each other. So if I said f of x is 5x, we'd multiply it by g of x, which is x plus 2. Remember, multiplying just means every part or every term of the first function gets multiplied to both parts. So this becomes 5x times x plus 5x times 2. And we're left with 5x squared and 10x. And then our last one would be if we've got one function divided by the other. So if we did that with our examples here, 5x divided by x plus 2. And on this one, we don't have anything to simplify, so that's all it is. Okay, and then there's something just to remind us about. We've seen this before, but I don't know how recently you've seen it. So here's what a power function is, another type of function. Anytime you have some coefficient times a variable to a power, where this is a integer or a number, this cannot be a variable, we call that a power function. So a power function is when the exponent is a number. So for example, if you had 7x to the 4th, that's a power function because there's a number in the exponent. Another one could be negative 2x to the negative 3. That's also a power function because there's a number in the exponent on the variable. So let's just say, for example, what if I had a couple power functions and I'm doing some operations with them? So I can see my operation here as addition, which, remember, addition, we're just combining like terms. Remember, like terms are the same variable to the same exact exponent. So do you see here that this x to the 1/2 is the same as this x to the 1/2? That means these are like terms, and we're going to combine them. So I've got 4 plus a negative 9 gives me a negative 5, of the same like term. Remember, when we're combining like terms, we're just combining them like you would add M&Ms or types of fruit. If you've got 5 M&Ms plus 10 M&Ms, that's 15 M&Ms. If you've got 4 apples minus 9 apples, that gives you negative 5 apples. If you've got 4 x to the 1/2 plus negative 9 x to the 1/2, that gives you negative 5 x to the 1/2. Okay, let's look at this one. So I see here that my operation is subtraction. Remember from before, subtraction means we're going to distribute it behind. So I'm going to make this a plus, and anything behind it is an opposite. Now subtracting that negative 9x to the 1/2 is like adding. Okay, now let's look for like terms. Do you see here that this x to the 1/2 is the same as this x to the 1/2? These are like terms. So we can add the 4x to the 1/2 and 9x to the 1/2. That gives me a total of 13x to the 1/2. Okay, now we've got a power function here, and we're multiplying. So we're using our multiplication property. And just keep in mind, you can rewrite this without the parentheses. So I could say this is 6 times x to the 3/4. Remember that anytime there's no power shown, there's an invisible x to the 1. And here, anytime we have a multiplication of 2 exponents, remember when we learned about those properties, multiplying exponents with the same base means we add the exponent. So this right here will become x to the 1 plus 3/4, which is really well. X to the 1 is like saying 4/4. So 4/4 plus 3/4 is x to the 7/4. And this 6 is just being multiplied in front. So our answer is 6 times x to the 7/4. Okay, and then lastly, we've got division, and this time it happens to have powers, a function of powers. So this is 6 times x over x to the 3/4. Keep in mind again, in a quotient of functions, as long as we have the same base, we can take, and actually I'm going to rewrite this 6 times x, I'm going to split it up. And I can split these up because they're being multiplied, and so you can put them in any order and it means the same thing. Remember that we're going to take this, and as long as they have the same base, which is x, I can subtract their exponent. So this x is really x to the 1. So we've got 6 times x to the 1 over x to the 3/4 is the same as saying x to the 1 minus 3/4 in the exponent. So this is really 6 times x to the 1/4 power. Okay, now let's talk about composition of functions. I think you might have seen this before in algebra, but in case you don't remember, here's what a composition of functions means. The composition of functions is a function of f where the function equals the inside function goes into an outside function. So here's what that means. Normally, if we just have one function, we have some value of x. And if I'm looking for f of x, I'll put in x inside that f of x. Well, a composition of functions means we take that first whole function and we put that whole value into this outside function of g. And I'll show you what that means. So just like if I'm giving you here that f of x equals x squared plus x, let's say I wanted to find f of 1. Then instead of x, every time I see x, I'm going to plug in 1. Instead of x, I'm going to plug in 1, okay? Which in turn would give us 1 squared is 1 plus 1 equals 2. So we know f of 1 is 2. Or I could say, okay, instead of f of x, I want you to find what's f of g. Anytime I see an x, I'm going to plug in a g instead. So f of g would be g squared plus g. Okay, so we're just replacing what that value of x was. So let's say, for example, if you've got f of x equals 2x minus 7, and if you've got g of x equals x squared plus 4, then what would be g of f of 3? So this is what we call that composition. So the first step is we're going to find the inside function. We're going to find f of 3. So f of x, remember they said was 2x minus 7. So f of 3 is going to be 2 times 3 minus 7, which is 6 minus 7, which is negative 1. So we know f of 3 really equals negative 1. So now that we've solved that, the second step is we're going to rewrite the composite function. So remember, the composite function was g of f of 3. Well, remember, f of 3 was really what? Negative 1. So I'm going to replace, instead of g of f of 3, I'm going to say this is really like saying g of negative 1, because f of 3 really is negative 1. So what would I do to find g of negative 1? Okay, well, g here is really x squared plus 4. So g of negative 1 is x, which is negative 1 squared plus 4. Now we're going to solve this. Negative 1 squared is positive 1, plus 4 is just 5. So g of negative 1 is 5, but we also remember that we really found this. So really g of f of 3 equals 5. And that's it for now. See you in class.